So no one has. So no one has joined till now. It's already 4. Let me wait for 2 to 3 minutes. We can start. Okay. So let me start presenting. So probably no one will join in the live session, but please go through the video lecture because this lecture will be recorded. I'll record it and I'll upload in the YouTube, and the link of that video will be uploaded in that weekly log sheet. So from there you can get access of that video, and please you can go through that video. Okay. So let me start by presenting my entire screen. Okay. So this is the course name, Fundamental of Statistical Thermodynamics. First, we'll discuss some basic question that was uploaded in the NPTEL portal as week 0 assignment 0. So these are some basic questions, but as these are uploaded, so I thought to mm, discuss this question as well. Okay. So now, so what is the first question? Thermodynamics deals with there are 4 options. Number 1, rates of the reaction. These are very basic question, I know, but still let me discuss. Second one is transformation of energies. Transformation of energies. Third option, oh, 1 minute because no one has joined. So, okay. Okay. The third option is probability of finding an electron. Prior, I was discussing this question. Thermodynamics deals with there are several options: rates of the reaction, transformation of energies. Third option is probability of finding an electron. finding an electron, and the fourth option is splitting of d orbitals in magnetic field. So it's very straightforward question. Thermodynamics essentially deals with the not rates of the reaction, because we know chemical kinetics deals with the rates of the reaction. Uh, this is the transformation of energies from heat to work. We can think like tran transformation between heat and work. So essentially thermodynamics deals with that. Okay. And the rest of the option was probability of finding an electron is essentially not related with the thermodynamics eventually. And splitting of d orbitals in magnetic field also is not the business of thermodynamics. So essentially the transformation of energy, this is the correct answer. So now going to the second question. The internal energy of a system is, okay, the internal energy of a system is, so now options are kinetic energy, then be potential energy, option C, sum of kinetic energy and potential energy, and option B, that is total energy of the system total energy of the system added up in all forms.
D.
Okay, exactly. D should be the correct answer, because we know that kinetic energy, potential energy, these are all different forms of the energy. But there are rest of energies like we know rotational
Vibrational
energy,
energy.
vibration energy. Yes, exactly. So the correct answer will be the total energies, all forms added up, all forms. Now the question number 3. These questions are very basic question, but these questions are uploaded as the week 0 assignment. That's why I'm discussing. The first law, and these questions are not related to statistical thermodynamics as well. These are basic classical thermodynamics. So, but it's better to discuss.
Okay.
The first law of thermodynamics. If you have any other doubt regarding the lectures uploaded in the last week, then you can also ask.
Okay, sir.
So, first law of thermodynamics can be expressed as, provided options are del delta U equals to Q plus W. Option B is delta U equals to delta S entropy change W plus W. Option C, delta U equals to delta H plus delta S. And option D, del G minus P delta S. So what will be the answer?
First option.
Yes, first option. Q is the heat and W is the water. So overall energy should be conserved. This is
In
the
physics, I think there is an different expression. So what is correct?
no, but in others, no, both are correct. That is totally due to a convention. In physics, what happens? Let's say if you have a system, uh, now heat is entering into the system, right? So in physics, we are looking from the surroundings that if heat is entering in the system, but in chemistry we are looking from the perspective of the system, and physics from the surroundings. That's why there is a convention of sign. Otherwise the overall theory will be same, because when you what is the difference? The W in physics, W is pdv or d cross W. But in chemistry, d cross W will be minus pdv. So that's why overall form will be the same. After putting the pdv, then the form will be the similar. But due to the convention, the form looks like different. Just plus W or minus W. That is the main difference. But that does not change the physics or phenomena. That will be remain same in both cases.
The del sign.
This del sign.
Yes.
No, these del sign we can write du. Du for the small change, and here it is for the large change. That's why it's written as delta, capital delta U. When you are writing in the capital form, capital delta U, then you essentially write Q or W. But if you write in du form, then you have to write d cross Q, d cross W in this way. These are signifying the small changes, but this is the large change.
Okay.
Just you can think we have integrated this from U1 to U2. Then you will essentially have U2 minus U1, and that is written as delta U, just like this.
Okay.
So this is question number 3. Again, I think this is also a very easy question. Increase in entropy of an insulated system leads to, okay, increase entropy of an insulated system leads to absence of exothermic process, endothermic process, spontaneous process mostly. So what will be the answer?
Spontaneous.
Yes. But how you can say this? Because this is an insulated system. We know for spontaneous process, what is the criteria? That del S universe should be greater or equals to 0, increase in. But here the entropy of the system is written, not the universe. Then how it can be said that it's a spontaneous process? Do you get my point?
Yes.
Now how you can say this? Insulated system.
Universe also
Yes, universe also.
insulated system.
Yes, insulated term here the or actually you want to mean the insulated is isolated. That means that is not interacting with other. So system is
Yes.
not interacting with surroundings. So in that case, obviously that you can think the universe, overall universe is as a system which is not interacting with others, because there is nothing beyond universe. So
Yes.
universe is can be considered as a isolated system. So from that perspective, you want to means that this is the del S universe. So it will be spontaneous process. And exothermic process, you know, the del H should be positive. Endothermic del H should be negative. And this is the non-spontaneous process. So correct answer will be the spontaneous one. Okay. for the process, it's also for the process to be spontaneous, the correct option. Same question. The correct option is option one. Okay. Del S is okay. Del S system equals to 0 and del S surroundings greater than 0. Greater or greater equals to greater than 0. So less than 0. Less than 0. Del S system dash surrounding greater than 0. Indeed, the system is 0. Surroundings also 0.
C.
See, because the that essentially means the del S universe. System plus
Yes.
surrounding should be the del S universe, so it will be the correct option. Okay. So these questions are uploaded in Jira 7. There are more other questions as well, but that I'm not going to discuss. Better to going questions related to the last the topic discussed in the last week, last classes, week one. Okay. This is question number 5. Now, so first I want to discuss this question is little bit a theoretical question you can think, uh, but after that I will discuss numerical exercise as well. Classify the statistics of the particles. Okay, so it is better to discuss first, then going I will discuss the other question. So what is the classification of the particles? Because we know there are essentially two types of things in the universe. One is particle, another one is wave. So here in statistical mechanics or statistical thermodynamics, we will deal with the particles, varieties types of particle. So essentially there are two types of particle. So the first one is classical particles. Okay, you can wait 1 minute. My pen does not have charge. 1 minute I can be charge. Just wait for one. Charges. Okay, let me connect it again. Yes. Okay. So better to deal, better write in different. Okay. So what was the question? Ah, yes, particles, right. So there are essentially two types of particle, as I discussed. First one is classical particles, and another one is we know quantum mechanical particle, or in short, quantum particles. Okay. So what is the difference between classical particle and quantum particle? Can you predict?
Size.
No, let's say I give you a particle A. So how you can say this is a classical particle or a quantum size? Yes, you can say, because in quantum mechanical particles, the size of the particles are in the microscopic level, and classical particle has the size of in macroscopic level. That's okay. But there is a basic difference between a quantum mechanical particle and a classical particle. So that is classical
By
particles
de
are
Broglie.
by de Broglie wavelength. You want to mean that in quantum particles there is a dual nature.
Yes.
Yes, yes, that's correct. That's also a way of, to distinguish. But by the definition, the classical particles are distinguishable. Do you hear this term distinguishable? And the quantum particles are indistinguishable. What does it mean? Because in question in statistical mechanics, directly classical particles or quantum particles will not be written. They will write in question distinguishable particle or indistinguishable particle. From that, you have to understand what kind of particle they are talking about. Okay, so basically, these are the indistinguishable particle.
What it means?
Huh. Distinguishable means, let's say you have two classical particles, two classical ball, similar kind of ball, identical ball you have. So can you distinguish this ball?
No.
You can distinguish. If you have the same kind of ball, you can distinguish those ball by their trajectories. Okay, let's say you in front of you there are two
Coordinates.
coordinates, because the coordinates are changing. In your hand, if you have two balls, let's say now in front of you, two balls are, let's say that two balls are mixed together, and now after that, if you anybody asked you to find out which one is first ball or second ball, you can say this, because you can track the fast ball. Let's say in your mind you put level 1 in one ball and another ball is level 2, then you can track the ball 1 or ball 2, which one is what. Okay,
But how they are completely same?
completely same. You have to keep the eyes on the fast ball. Let's say this is a ball 1, let's say this is the ball 1, and you fix your eyes on the ball 1. Then let's say after that it's mixed up and here it ends. So then this is 1 and this is 2, you can find out now which one is the ball 1 or ball 2, because
Okay.
while the trajectory is changing, you can see the ball 1 or ball 2, you can distinguish ball 1 and ball 2. First you
Yes.
have to
Yes.
level it, then from that level you can distinguish. So basically, if it is identical, because there are two terms, this is very important: identical and distinguishable. Identical and distinguishable does not mean similar. Identical means they look same. But in classical particles, if though particles are identical, then also you can distinguish that particles by their trajectories. So classical particles are always distinguishable, but quantum mechanical particles are indistinguishable. Now, instead of balls, you have electrons. Can you now distinguish? Because electron does not have any trajectories, because it has also wave nature, so it is just forming a wave, and both waves are there, let's say. Then how you can distinguish both electrons, which one is which? Can you
No.
understand? So in that case, quantum mechanical particles are not, you can't distinguish quantum mechanical particles, and these particles are essentially identical. So that's why for quantum mechanical particle, that overall study, statistical mechanics will be very different. For classical particles, this statistics is basically called as Maxwell-Boltzmann statistics, or MB in short, Maxwell-Boltzmann statistics, right? MB statistics. Now in quantum mechanical particles, now there is also two classification. First one is this thing, I think you have heard, bosons and fermions. Okay. Two types of quantum mechanical particles are there. One is boson. Bosonic particles essentially follows the Bose-Einstein distribution, or Bose-Einstein statistics. Whereas fermions follows Fermi-Dirac statistics, FD. So essentially, we will study in statistical mechanics three types of statistics: Maxwell-Boltzmann for distinguishable classical particle, Bose-Einstein for bosons, which are quantum mechanical particle, and Fermi-Dirac statistics, which are fermions. So three types of statistics are there. Okay. So what is the difference between boson and fermion? Do you know?
Full spin, half spin, minus
Exactly.
half, and it's minus.
Uh-huh. Bosons have the full integral spin, and fermions have the half integral. These are the basic difference. Also, there are lots of difference, but the basic difference is by which you can categorize bosons and fermions. That's their spin, full integral spin and half integral spin. Okay. So now I think this is the this is clear. Now going to the next question. This is kind of theoretical question. Now we'll discuss some mathematical questions. Question number 7. Okay. Find out the number of ways by which 10 students can be grouped in three categories such that first and second group contains same number of students. Okay. This is very basic question. So there are 10 students. Now you have to group 10 students in three categories. Let's say we can name it A, B, and C. three groups you have to create from 10 students, and the criteria is that first and second group must have the same number of students. So what will be the probable options? We have to find out first the uh, orientation or the configuration, that we have to first find out. Then we have to find out the number of uh, the weightage W. If you've gone through the lectures, the W has been discussed. For particular instantaneous
Yes.
orientation, there are we can calculate W, but that is for the particular orientation. But we have to first figure out the number of orientation, or which are the probable orientation, that we have to first figure out. And for under every orientation, we have to calculate the number of ways how you can how the number the microstate. And I don't want to use the term, but the term is called microstate, the number of microstate, or the weightage of that way orientation you can figure out. So first, let's say in first, what is the option? Let's say we can write it like in this way. First
118.
orientation, or 0010.
Yes.
First one is 0010, correct? So now the weightage of this configuration 0010 will be
10 factorial by 0 factorial 0 factorial 10 factorial.
exactly. So obviously this one. Next is 118. So just we have to calculate it. So it will be 90. 226. So what will be this? 10 90 into 8 into 7/4. So now you just use 90 into 14. What you can use the 90 into 14. It is 1260. 334. So it will be this. So what will be that? 3 10 factorial by, okay. Just you can use the calculator directly, but let me 10
Okay, I'm
factorial.
using.
So what will be the answer?
Please wait. 4200.
This one. And the next one?
Yes. 3150.
3150.
Yes.
3150 at the last. 10 factorial by 5 factorial, 5 factorial.
252.
Okay, so this will be the total number of. Now you have to add for the total number of uh, ways. So one more thing is clear from this. This configuration is most probable configuration 334. Okay, so how you can identify the most probable configuration? It's very straightforward, that you have to find out the probability. Total number of configuration, just you have to find out W. W will be the sum of all W's. And for any configuration, let's say this 334, what will be the probability of W334? It will be just W334 divided by W. And obviously this will be the maximum among these all configuration, and that's why it's called the most probable configuration. Okay, so now
W is 8953.
Total W is 8953. So from here you can calculate the percentage, the probability uh, for each configuration. So what is the role of this most probable configuration? That you can see here, just we have 10 molecules, right? 10 student, not molecule. But if you consider the large number of molecules, later you will see that in case of large number molecule, there will be lots of possible configuration will be there, lots of possible configuration. Here, the lots of possible configuration are orientation are 1, 2, 3, 4, 5, 6, 6. But if you have, let's say, 1,000 possible configuration, then how you can deal? You have a system, macroscopic system, let's say, with a gas. There are avocado number of molecules, so there will be infinite number of orientation, and for each orientation there will be a several. There will be under each orientation there will be infinite number of ways, probable number of ways. So how you can deal with those problems? For that cases, what happens from here you can see the most probable condition is this with the value 4200. But if the number increases significantly, then it actually looks like this. The plot, if you plot that like this, do you know the delta function?
No.
Okay, so it will look like a delta function. Delta function means, let's say, if fx is a function, fx is a function such that it will be infinity when x equal to 0, and it will be 0 when x not equals to 0. Then how it will look? Okay, so then how it will look, that fx, that when x, let's say this is 0, x equal to 0, then when x equal to 0, then only it is infinity, but for other values it is 0. So just there is a peak at x equal to 0, and after for the rest of the all values it is 0. This kind of function is called the delta function, and it is written like delta, delta x. So that means, what does it mean? It will look like a delta function means only for a particular configuration the probability will be infinity, and for other configuration uh, the probability will be 0. So for this kind of cases, for a particular configuration, which configuration I am not talking about, it will be discussed in later classes, but for a particular configuration the probability will be infinite relative to the other configuration. Other configuration you can consider 0, and for that particular configuration the probability you can consider infinite. So it is very straightforward in that case. Just like let's say these are all, just you can think like this, these are the same values but this is just like this. Then you can think this is the main configuration, you can ignore other configuration. This is just like delta function like this. So for that cases you have to deal with that most probable configuration. So later it will be discussed probably in future lectures. So this is in this way you can directly calculate. Okay, this was our question number 7. Question number 8. This is also very straightforward question. Consider the accurate Starling formula and derive the Starling approximation for large values of x or variable. This is the first question, and second question is also included with this. Find out the error obtained due to Stirling formula with the 10 sample size. Okay, so this is the question. So first you have to write down the actual Stirling formula. That means there is not approximation, the formula. So what is the formula? You know, x factorial. X is a variable, obviously. X factorial is essentially root
X
over.
ln x minus x.
No, that is approximation. Here first we have to write down the formula, then we have to derive the approximation for large values of variable. Okay, that I will come into that. So the actual formula is x factorial equals to root over 2 pi, not x close to x to the power x plus half e to the power minus x. So this is the formula, original formula given by the Stirling. Okay, now you have to derive the Stirling approximation, which you are saying that is a Stirling approximation, not the Stirling formula. So this is Stirling formula. Now you can do it. Just take the log in both sides. Then it will be ln root over 2 pi plus ln t power half, and this is minus x. Correct. So you can write it ln root over 2 pi plus x plus half ln x minus x. Okay. Now you consider the x is very large. The Stirling approximation is valid only for the large values of x. This formula is valid for any values of x. You can use this. This is more precise formula. But the approximation is basically give the correct result when the x is large. So consider the x is large. It was also written here. So if x is large, then obviously you can ignore this term. This value will be you can calculate. So this will be very small value compared to this. So just which term will be there? X ln x minus x. Because we have ignored these two terms, ln root 2 pi and plus half ln x. So this half is very x plus half, you can write x plus half directly as x. This can be written x plus half can be written as x because x is very large. So this will be x ln x and this is minus x, and this ln root over 2 pi will be very small compared to x and both x ln x. So that part also you can ignore. So when x is very large, you can write ln x factorial equal to x ln x minus x. This is our Stirling approximation, which we basically use. So now you can calculate the error by using this formula or the original formula. Okay, direct you can calculate. Okay, so now let's say for, I think this will be very large, 10, let's say 5. For 5 you can do it. Means put x equal to 5. Then what will be the ln x factorial? Original value of ln x factorial will be ln 5 factorial. What will be the value? ln 5 factorial. 5 factorial means 5 into 4, 20.
120.
So ln 120, what is the value of ln 120? If you have the calculator, you can, because I don't have the calculator, I have to be using your phone. ln 120. Let, so it is 2.484. This is the original.
4.787.
Okay, 120. Sorry, I 4.787. Right. Sorry. 4.7874. So this is the original value of ln5. Now use the Stirling formula. Stirling formula says it will be equals to x ln x minus x. So 5 ln 5 minus 5. So what will be the value? Ln 5
1.609.
minus, no, overall value, this value. This will be 3.04718.
Yes.
So now you can see the difference. This is 4, this is 3. So there is a difference because x is not here a real huge number. This is not. We have considered the approximation, but that approximation is valid only for the large value of x. But we are considering x equal to only 5. You can check if you use the x equal to 50, then the value will be more closer. Now, if you use the original Stirling formula, not the approximation, then what will be the value? According to that formula, this is the formula x factorial equals to this. So in that case, uh, x factorial is essentially the 5 factorial, which is 120. And Stirling formula says that this will be the value root over 2 pi, root over 2 pi, then x into x to the power half into to the power minus x. So it will be root over 2 pi 5 to the power 5 plus half, okay, into the power minus 5. So now if you calculate this value, what will be this? This is root over 2 pi 5 plus 5 into, so it will be essentially 5 to the power 5.5. So it is
6987.71.
6,987.712 and e to the power minus 5.
0.00673.
So let me 0.00673.
673.
So it is root over 2 pi. To the multiplication, this will give us 47.02730. So now multiply it with root over of 2 pi. So it is 11787. So now you can see this value is very much close. If you if calculate the error, then error will be 120 minus 1679 divided by 120. So it will be 7.89 divided by 120. So it is 0.2121. That means 2% error. So here the error is very large. If you calculate this error also, this error will be 30% error, probably close to the 35% error. But if you use the original Stirling formula, that in that case error is very less, 2%. Because if the sample size is x equal to 10, we know that for x equal to 10, the error is less than 1% essentially. So it's better to use this formula when the sample size is small. But if the x is very large, then you can easily use this Stirling approximation, this formula. That's why it's called Stirling approximation. And this is the Stirling formula. So, but in our statistical mechanics, essentially we are dealing with the large number of particles. So that's why x, because we know in 1 mole there is Avogadro number of particles. So essentially x is very, very large. So for that cases, obviously you can use Stirling approximation without any doubt. Error will be very, very less. Okay. Now, next question. Question number was 9. if there are m number of states, okay, and n number of distinguishable particle, then what will be the number of microstates? Okay. Though microstate is not defined in the class, but this is just the number of ways, number of arrangement, nothing more than that. So better is write the number of arrangements. Okay. So m number of states. Let's say there are m number of states, and if you have n number of particles, there are, and distinguishable means you can distinguish all particles. These are the classical particles, as I discussed earlier. In question, basically it has written as it will be written as distinguishable or indistinguishable. So basically, in starting in basic statistical thermodynamics, we will deal with the classical particles which are distinguishable, because in case of indistinguishable particle, the calculation are not very straightforward. Even for fermionic cases, it is very difficult to calculate. Okay, so here n number of particles. Now you have to find out the number of arrangements. Okay, so how you can, let me write the W. You know the W, the weighted factor, that is eventually the number of microstate, or you can write the number of arrangement, whatever you want. So what will be the W? So this is from we can solve this problem by our knowledge of permutation combination. Let's say for fast particle. For fast particle, there are m number of states. So you can, there will be m number of ways by which you can arrange that particle in that m number of state. So for fast particle, there will be m number of arrangements. Now for second particle, how many seats will be there? How many probable seats will be there?
M minus 1.
No, that is the problem. Na? That will be also m, because there is nothing mentioned that in one state there will be only one particle. In one state also there will be all particles can be there. Okay,
But this is already occupied by one particle.
particle, yes. So what? In why it is mentioned that in one level there will be only one particle. That is a
Okay,
restriction. You are
okay.
giving a restriction. That restriction is not considered enough. If you consider that restriction, that is a problem. Now, in fermions, there is a inbuilt restriction. You know Pauli exclusion principle, right? That is
Yes.
for electron. Electron is a fermion. That what is that exclusion principle? In one single energy level, two particles cannot be there. So in every one level, there will be only one electron. So that restriction comes in with the fermion definition of the fermionic particle. So that's why I said that for fermions it is very difficult to calculate. But here it is our clear distinguishable particle. So it will be just for, so there will be for each particle. So m probabilities will be there. So essentially there are n number of particles. So that will be m to the power n. This is the total number of probable arrangements. So now you are saying that let's say, also let me discuss that part as well, as you mentioned. If one state can occupy only one particle, now what will be the W? For first particle, the number of probable seats are m, but for second one, it is m minus 1. For third one is m minus 2, and it will be goes up to,
1.
no, there are n number of particles,
M minus n.
m minus n minus 1.
Yes.
Okay, because for first particle, it is m minus 0. For second particle, it is m minus 1. For third particle, it is m minus 2. So in general, it is m minus n minus 1. Clear?
Okay.
So this is our total number of arrangements, W. So you can modify this form. Now you can add this up to 1. And you can divide it, rest of the term, m minus n into n minus n plus 1, and so on up to 3 to 1. So the numerator will be m factorial, right? And the
Yes.
denominator is m minus n factorial. What does it mean?
MPN.
MPN. This is the definition of our number of permutation. So when we studied this number of permutation, we actually use this condition that in one state only one particle can occupy. So this will be the number of W. Okay. Now, so this question is clear. So going to the next question. This question can be done easily. Okay. It was question number 9. In how many ways four particles can be arranged? Four particles which are Maxwell-Boltzmann particle in the energy levels with the energy 0, epsilon, and 2 epsilon, such that total energy is 4 epsilon. Can you do this? I give you 2 minutes. If you try it, otherwise I will
Okay.
discuss.
I can place more than one in same energy level.
Yes, Maxwell-Boltzmann particle, no restrictions are there.
Three.
3. How?
040 202 121.
040 202 and 121. Yes, but now you have to calculate the W, the weightage factor for each
Okay.
configuration. You have just calculated the number of orientation.
19.
Exactly. Correct. Okay, let me also discuss this. And easy actually. There are three energy levels. Epsilon 1, that is 0. The energy of that level is 0. This energy has the energy of epsilon, and this is the 2 epsilon. Now you have the four particles. Yes, four particles. You have to arrange those particles such that the total energy should be the 4 epsilon. So one probability is that you can put uh, two particles here and two particles here. So it is essentially signifies 2, 0, 2, and the W will be 4 factorial divided by 2 factorial, 0 factorial into 2 factorial. So essentially it is 6. Okay, this is one orientation. What will be the other? One orientation can be this 0 here, 2, 1. The total energy will be 2 epsilon. Yes. So total energy is 4 epsilon. So here the W will be W. Okay. So it will be 12, and one more probable orientation is there. That is all particles are here. So 0, 4, 0. So it will be essentially 1. The total number of W is 1, 12, 6. This is the total number of ways or arrangements. So now this is our most probable arrangement. This is our most probable arrangement. Okay. So this is this type of question can be asked in NET or GATE. This type of question are very frequent, and these are very easy also. Just you have to keep in mind that whether it is Maxwell boson particle or the Fermi-Dirac distribution following fermions or bosons. These are some tricks are there. Otherwise, it's easy. So let me clear it also that we are using this formula, right? The W, the okay, is W the weightage factor of the number of arrangements under a particular instantaneous configuration. That is the W. It's also discussed. This is our n factorial divided by n1 factorial, n2 factorial, n3 factorial, and such, and it goes on, right? Like this. So you can write it by this notation. You know this notation?
Yes.
Okay, then it's easy. So this notation you can write, but you have to keep in mind that this formula is for only Maxwell Boltzmann particles. Means you are considering the particles are
In
distinguishable, distinguishable, not indistinguishable. How? Let's consider this. If 1 minute, someone is joining. Okay, it is connected. Yes, now it will be connected. So okay, so let's say this configuration, right? This 202. Now we are considering the particles are distinguishable. Means four particles are there, A, B, C, D. Tagged those particles A, B, C, D. Then only you can distinguish, right? So what we have written, there are 6 number of probable arrangements under this orientation. How you can write this? A, B, C, D, or A, C, B, D, A, D, CB, or there are CD, AB,
All
CA,
reverse.
all reversal, BD. So essentially there will be uh,
6.
6 CD, AB. So now if let's say all particles are indistinguishable, then what will be the number of orientation under this configuration? Number of arrangements. How many number of arrangements will be there? Let's say there is no ABCD, no tag. Particles are indistinguishable. You can't distinguish between A, B, C, D. All are like a ball. Then what will be the number of arrangements?
Only one.
Only one. Exactly. So for Maxwell-Boltzmann particle, the number of arrangements will be much more higher compared to the quantum mechanical particle. Okay, so it's clear that this formula will not be valid for quantum mechanical particle. For that, we have to consider the reference formula. Before that, we have to modify this formula as well. This formula is valid uh, until there is no degeneracy. If there is a degeneracy, you have to consider that degeneracy as well. Okay. Till now, the example we have discussed or discussed in the class, in all cases, there was no degeneracy. That's why the formula was correct. But when the degeneracy appears, you have to consider we have to modify the formula slight. That W Maxwell Boltzmann will be clearly n factorial pi I gi to the power ni divided by ni factorial. This is our formula when there is a orientation. Now, if there is no there is no degeneracy, let's say gi is equal to 1 for each I. If gi is equal to 1, so easily you can write it n factorial into 1 by ni factorial. That essentially means that n factorial. So this formula we know. But when there is a degeneracy, you have to consider the general formula. So this is our main formula. Okay. Now for Bose-Einstein and this is for classical particle or Maxwell-Boltzmann particle. That's why in starting I have discussed the types of particle. Otherwise, everything will be very confusing. It's better to first clarify the types of particle, then it's better to discuss the types of statistics. So the Bose-Einstein statistics, in case of Bose-Einstein statistics, there are derivation of these formulas as well. You can look at in the books, but it's not important. It's quite difficult. So there will be for Bose-Einstein, the formula will be Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. This will be the formula. Okay. This is for
Is the derivation of the first formula important?
no. You can derivation is not important, but you can think this is very easy. For this formula, the derivation, the essence is very easy, that if there is n particle, total n particle, you know the number of arrangements, that will be essentially n factorial, you know, because n into n minus 1 into n minus 2 and such that, so it will give n factorial. And if there are, let's say, two groups, n1 and n2, for each groups the number of orientation will be n1 factorial, n2 factorial. So if you find out the number of ways by which you are categorize the groups, obviously you have to divide. So this is not very straightforward derivation, but you can feel the derivation. But for these cases, the derivation are very tricky because you have to consider that fact. Mm, Here you can do it manually without using the derivation. If all particles are identical, then indistinguishable, then it will be one. But it will be not very easy for other cases as well. That's why that these derivations are quite tricky. And the Fermi Dirac is, and these are for all for under a particular orientation, under a particular orientation or configuration. Is gi factorial divided by n factorial gi minus n factorial. These are for formulas. Okay. So this formula it's better to remember because in competitive exam like NET and GATE, not only Maxwell Boltzmann is asked. In 90% cases, the Maxwell Boltzmann is asked, but sometimes they can ask the Bose-Einstein or Fermi-Dirac. If you don't know the formula, then you have to do manual. Otherwise, there is no option. Okay.
Can I take screenshot?
Yes, and this lecture note will be uploaded and the videos will be uploaded in the spreadsheet. You can take the screenshot, no issue.
Okay.
Okay. So there is a direct consequences of this formula of Bose-Einstein and Fermi-Dirac. Let's say GI is here we discuss now if GI is 1, if there is no degeneracy, you have reduced the formula, right? The in our known formula. For here also, let's say for boson, GI is 1 for all G, for all ith level. So first, okay, one thing I think it should be clear in class also it was discussed that states and levels are different. Okay, states and levels are not the same. What is the difference between states and levels?
Please explain.
Okay, so states, let's say there are these are three, these are energy levels, right? Like this, or epsilon 1, epsilon 0, epsilon 1, epsilon 2. These are energy states or levels. What is the correct? These are energy levels. Now, here levels are state are same. But if there is a degeneracy, then this definition will be different. Let's say here there is a degeneracy. So now there, how many levels are there? Three energy levels: epsilon 0, epsilon 1, and epsilon 2. But how many states are there? Four. Four energy states are there. Okay. So if there is, let's say, I number of energy levels for states, you have to consider the degeneracy as well. So only when Gi is equal to 1, then only the states and levels are equal. Otherwise, you have to consider the G. So here
When there is
the
no degeneracy.
no degeneracy. If there is no degeneracy, then in that case the levels are 3, states are 3. No issue. So that's why it's better to write in the formula Gi epsilon I, total energy if you calculate. This is the total energy, Gi epsilon I. Here this I are the levels. Okay. But if you use this formula, this is here I is the states. Let me give an example. This is very confusing because when I was studying, this confusion was also appeared to me. Let's say these three energy levels we are taking. This energy is 0, this energy is 1, and this is 2. So under this case, let's say what will be the total energy? Total, in each cases there is a one particle. So total energy will be 0, 1 into 0 plus 1 into 1 plus 1 into 2. So total energy essentially will be 3. So formula is just we did Ni. Ni is the number of particles in the ith level into epsilon I. That means the energy of the ith level. So from here you can write this. Here this I are the same for level and state are same because there is no degeneracy. Now if you count the degeneracy, let's say there is a degeneracy in this level. So it is 0, it is 1, it is 2. So what will be the now energy? In each level there is a one particle. So now you have to calculate 0 into 0 plus here two particles are there. So 1 into 1 plus 1 into 1 plus 1 into 2. So it will be 4. So what you did? Summation over I, Ni, epsilon I you did, but here I are the states. All states. 4 states are there. 1, 2, 3, 4. All states are there. But if you consider as a level, just you have to do Ni, epsilon I, where these I are the levels. Then how you can write it? That E will be 0 into 0. Down the formula will be Gi will be there. So plus, what is Gi here? 2. Ni is 1 and epsilon I is 1, and it is 1 into 1 into 2. So here it is 4. So just when you are considering the levels, this will be come it together as this form by including this GI. So when it is summed over level, obviously there will be written as level. If there is nothing written as level, you have to consider the states. Or you can see by using this G. If there is G, obviously they are considering the summation over the levels, not over the states.
If there is a restriction that no two particle can stay in same level, then
Mhm.
can I think
Same.
it's degenerate?
Please repeat it again.
If there is restriction that I cannot place two particle in one level,
Level or
then
state?
state,
One state. Okay.
then can I think degeneracy? Means
Yes. 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 Obviously, there will be various level. Like, let's say you study the rotational spectroscopy.
no, I'm in BSc first year only.
Okay, it will be in BSc second or third year. Okay, so let's say if they are in rotational, if they are this type of degeneracy will be there. This will increased. If the levels increase, the degeneracy also increased in rotational spec. In if these are the rotational energy, this increase 2j plus 1 is the degeneracy for jth level. Okay, so degeneracy may be there. There is nothing related with the degeneracy and the number of occupancy. Number of occupancy is, depends on the type of particle, which type of particle you are taking or which type of physical system you are dealing with. But the labels are totally dealing depends on the degeneracy totally depends on the type of energy, whether it is vibrational, translational, or rotational, this or any electronic energy or magnetic field is there. As you know, for hydrogen spectrum, there is two energy levels. These are degenerate, right? Plus half and minus half. When magnetic
Yes.
field is there, then only they are become non-degenerate. So degeneracy depends on the external condition also. That does not related with the occupancy. So this formula is safe. This formula you can use for general cases when there is degeneracy. So now here, from here you can see if there is no degenerate level, if Gi equal to 1, what was I discussing? For bosonic case, what will be the reduced formula? Let's say. For bosons first, let's say Gi equals to 1. So if Gi equals to 1 for all levels, uh, because we are considering I here, that means we are considering the levels, not the states. G, we are considering G. So what will be the WBE? It will be Ni plus 1 minus 1 factorial divided by Ni factorial. Gi is 1, so 1 minus 1 factorial. Okay, so it is correct.
Okay.
So for if there is no degeneracy in quantum mechanical particle in a level, there is no degeneracy, so you can directly write down there will be only one orientation. You can see from this expression, this example, there is no degeneracy, right? So that's why how many orientations that may be there for the classical case, for Maxwell-Boltzmann case, if the particles become the indistinguishable, all probability goes will be converged into the same orientation. That will be the only one orientation.
For quantum particles.
Obviously, data should be indistinguishable. Quantum particles are indistinguishable, as we have discussed earlier. If the particle can you can distinguish, then it will be the Maxwell-Boltzmann. Then six orientation will be there under this configuration, right?
Yes.
So we have to consider the indistinguishable particles when uh, quantum mechanical particles are written. Okay,
If there is two different quantum particles,
they are also indistinguishable. Quantum mechanical particles all are all are indistinguishable. Let's
two
say
different.
yes, two different particles. Let's say one is proton, one is electron. Both are fermions, right? Both have half integral spin. Both are indistinguishable. How you can distinguish proton and electron? By their charge only you can distinguish. But when they are occupying a level, although proton and electron can't occupy the level, let's say positron and proton, how you can distinguish? Right? So that can't be distinguished. When the quantum mechanical particles are there, you can't distinguish. Only
Okay.
if there is degeneracy, then only WB will be more than one. Otherwise, it will be. 1. Now let's see for fermions. If you put J equal to 1, you 1 factorial divided by Ni factorial Gi minus Ni. So 1 minus Ni factorial. So here you can't say that will be 1 only. You can't say for bosons it was straightforward. But in that case, this will be the reduced formula. Okay. Okay. But from here also, you can do, just look at this term. You can also reduce. This is 1 minus Ni, right? Correct? So
Yes.
now, you know that the term was Gi minus Ni factorial. What does it mean? Gi must be greater equals to Ni. Correct?
Yes.
Why?
N cannot be negative. What is inside the factorial?
That is mathematical. Now, if you take
Yes.
physically, for any level, let's say there are degeneracy, 5 degenerate level, 6 degenerate level. So G is 6. So now how many particles can be there? Maximum 6 particle can be there, because fermion, we know that for each state there will be maximum 1 particle. That is Pauli exclusion principle.
Yes.
So maximum particle will be 6. So Ni should be always less equals to Gi.
Okay.
Yeah. That's why that appears there. Okay. So now here, what is the probability then? One thing, it would be Ni equals to 1. In that case, it will be 0 factorial, or it can be Ni equals to 0. Then it will be 1
1
factorial. So
factorial.
both are
1.
1. So both are 1. So then what will be the WFD? WFD will be in
1
both
by n
probability,
factorial.
1 factorial by, in first cases, Ni is also 1. So 1 factorial into 0 factorial, that is 1.
1.
And for second cases also, it is 1 factorial divided by 0 factorial into 1 factorial, that is also 1. So if there is no degeneracy for fermionic particle also, there will be no other orientation factor, weightage factor, that will be 1. So from equation, it can't be solved directly, but if you input this logic, then it is straightforward. Okay. Because when in that case we did not consider the particle as boson or fermion, we just consider the particle as indistinguishable. Just by using that, we have obtained there will be only one orientation. So it should be valid for both boson and fermion. So boson and fermion, in both cases, if there is no degeneracy, then obviously there will be one configuration under each orientation. Okay. So now this question is clear. These are used for solving the numerical problem as well. You have to keep in mind these formulas. It's not very difficult to remember. So it was question number 10.
What is the easy way for remember?
Just you have to remember, like these are like this is something like permutation formula, right?
Yes.
Just look at, and this we have to explicitly remember. But the form you can see, just divided the numerator in two parts, Ni factorial and Gi minus 1 factorial.
Yes. Easy.
It's not very much difficult. Okay, so question number 11. What is, okay, this question has been solved in the class, if you guess. So let me discuss. If there are two energy levels with degeneracy 3 and 2. The number of elements we can have with two particles in ground state and three particles in excited state. Okay, try. Just you have to
E is
use
for
a
ground state.
yes, yes. Two energy levels are there, epsilon and 2 epsilon. So ground state energy is epsilon and excited state energy is 2 epsilon. Just you have to use the general formula. Okay, one more thing. If there is not mentioned the particle as quantum or classical, distinguishable, then by default you have to consider the Maxwell-Boltzmann statistics, the distinguishable particle.
Why?
That is just question because in syllabus it's generally we have Maxwell-Boltzmann. Now nowadays to make the question more harder, they are including the bosonic and fermionic. Otherwise, you will if you do that, you will not have option regarding bosonic and fermionic.
10.
10. No, no. Total W.
There is only one combination possible because it is already mentioned two
So
particle
already
in ground.
mentioned. Hmm. Now you have to use the formula. Okay, probably one. Everything. Enough for the- Hmm. Okay, let me do it. There are two energy levels, right? For ground state, the degeneracy is 3. For fast excited state, degeneracy is 2. The energy of ground state epsilon, it is 2 epsilon. Now, uh, two particles in ground state. So, N1 is 2. We don't know in which state it is there, but in grounds means level here, though it is written state, but as they are discussing with the degeneracy, so it means the level. Okay. Mm. So Ni is 2 and N1 is 2 and N2 is 3. So just you have to put the formula for the value. W is Ni factorial 5 over I Gi to the power Ni divided by Ni factorial. So just open the pi. So it will be G1 to the power N1 divided by N1 factorial into G2 to the power N2 divided by N2 factorial. Okay. So what is N? N is total number of particles, that will
5.
be 5. 5 factorial. Gi, what is Gi? Gi G1. G1 is 3,
3.
and G2 is 2. So it is 3 to the power G1 to the power n1. So 3 to the power 2 divided by n1 factorial means 2 factorial. And it is 2 to the power 3 divided by 3 factorial. Correct? So it will be 5 factorial, 3 factorial will be there. So it is 10. And it is 3 to the power 2, 2 to the power 3. So 10 into 9 into 8. What will be? 720. Clear?
Yes.
So what was the mistake?
In the middle part,
Okay. Okay.
GI by
So
NI.
okay. So this you have to remember. It's better to remember the number of states equals to degeneracy into the number of levels. Correct? Here the number of states are how many? 3, right?
6.
Total, not total, for each level or each
Okay,
state.
okay.
Okay, so then it is 3. So how you can obtain the number of states? Just degeneracy into level. Level is always 1 for each level. So just you have to multiply the degeneracy. Not need to remember. These are very straightforward. So it is question number 12. So let me see. Okay, this is very easy question, but still let me write. The number of ways in which four molecules can be distributed into different energy levels. What will be the answer?
How many molecules can in one energy level?
Any number of molecules can be there because if there is restriction, that will be mentioned in the question. As in the question, there is no restriction as mentioned, so essentially it means any number of molecule can do anything.
4 factorial by 2 factorial.
Exactly. So how we did it? 4 factorial by 2 factorial. No, that is under consider condition, under the condition in which in one particular level there will be only one molecule, but that is not in general, right? So what does four molecules are there, so number of molecules is 4 and number of energy level is 2. So you know W is m to the power n, so 2 to the power 4, so it 2 to the power 4
16.
16. And under that condition, when in one particular level there will be only one molecule, the formula is NPM. That means m factorial by n factorial into m minus n, uh, m minus n. So then it will be 4 factorial by 2 factorial. So it will be then, okay. So you have to be very careful whether
When
there is
there is mentioned nothing, then
nothing,
I
no
think
condition, then directly you have to use this, and you will get 4 marks in CSI or 2 marks, because this type of easy question are there. It's asked, but they will form the question very critically. The question will not be written straightforward like this. They will give some physical system, some these rotational energy levels or these energy levels, this molecule. These will be there. These they will confuse you. But the calculation part will be very straightforward. Okay. Next question is okay. This is very important question. Using Boltzmann distribution, Boltzmann means Maxwell Boltzmann. Okay. In the lectures of the first week that are essentially discussed about the Boltzmann distribution. That means they are considering the distinguishable particle, classical particle. Okay. Distribution, the probability of an oscillator in harmonic oscillator occupying the first three levels, which are n equals to 0, 1, 2, is found. Probability are given that P0 is 0.633, P1 is 0.233, P2 is 0.086. The probability of finding an oscillator in energy levels in n greater equals to 3. Clear? Question is there,
Okay.
right? It's just formed difficult. It's formed like that. The question is very difficult. There's lots of stuff, but it's very easy.
How to solve it?
Okay. So what in the first class also the probability has discussed. What is the form of probability? Probability means the number of, let's say there is a ith level. In ith level, there is a ni number of molecules. Then the finding a molecule in the ith level is essentially ni by total
Total.
number of molecules, capital N. So this is the probability, right? So if you sum it, we know it. What will be the sum over summation of probability of all states? It will be, you can write it, 1. Total probability must be 1.
Yes.
This is the definition of probability. Okay. So if the total probabilities must be 1, so you can write it as P0 plus P1 plus P2 plus P in greater equals to 3. Correct?
Yes. Yes.
So that is 1. So now you have to calculate this part. This is very
Okay.
straightforward question. 1 minus P0 minus P1 minus P2. So just you have to calculate it. It will be
Very easy probability question.
uh, just you have to keep in mind that overall probability should be 1. Just then you have to subtract. Means like 2. So it will be 0.048.
The language is very complicated.
This is the problem in the exam like NET and GATE. The language are complicated, but if you understand the language, that's why you have to read several times. Then essentially you will understand the inner meaning of the language. Then not for all question, but maximum question can be solved easily, especially from the physical part. 30 it is now 14. Okay, you can find a difficult question. So this you can also do. Hmm. This is also straightforward. Okay, this will send to later. First, let's say N non-interacting molecules. Oh, we are all in all throughout the discussion we are considering the non-interacting molecule. In class also sir mentioned that molecules and particles are non-interacting, because in case of interacting particles the statistical mechanics become very difficult. So it's essentially considered as non-interacting molecules or particles. Are distributed among three non-degenerate levels having energy epsilon 0 is 0, epsilon 1 is 8 into 10 to the power minus 21 joule, epsilon 2 is 2.7576, 21 joule at 100K. The average total energy, okay, of the system at this temperature is this joule, then the number of molecules will be, okay. So there are n number of molecules are there and three non-degenerate levels. So there are, let's say this is epsilon. Consider this as epsilon and this is 2 epsilon because it is just twice of this, right? So there are three energy levels: 0, epsilon, 2 epsilon, having this value of epsilon at 100K. If the average total energy of the system is given, then we have to find out the number of particles. You want to try it?
I'm not getting this.
The question means that this is our physical picture. There are three levels: 0, epsilon, and 2 epsilon. Now, in previous question, we know the number of particles like this. Here, that is not mentioned. Total number of particles we don't know.
That's
N
why
is N we have to find out. N is the total number of particles. Okay, but that we have to find out the explicit value of N. That the average energy of the system has been given. So just we have to use that. Let's say what will be the average energy. Okay. Before that, what is the value? This is a sign of averaging, right? You can use this sign or this sign. Both means the average or mean, whatever you want to mean. So what is the formula of average? How do you calculate the average mean?
total energy by number of particles.
Total energy by number of particles. So it essentially means that total energy, that is I Ni epsilon I, because all states are non-degenerate, so we can use states and levels in the same meaning. Okay. Otherwise, we have to consider the G divided by total number of particles. That is this Ni.
Yes,
So how you can now calculate this? So you can write it. Let's say you can take an example, a normal numerical example from which you can do it. Okay. Let's say uh, any batsman, he makes runs like in 10 matches, he makes run 50. This is matches, this is run. In 5 matches, he makes 0. In 2 matches, he makes 10. and 7 in one matches he makes 100, and in other two matches he makes 20. So how you calculate the average run? Just you have to calculate like this. Average run will be,
Total run by total match.
so mi into ri, sum over this, divided by sum over mi,
Total match.
total match. So it will be essentially 10 into 50 plus 5 into 0 plus 2 into 10 plus 1 into 100 plus 2 into 40. Okay. And this is total match, or we can write it M, capital M. So capital M is 20. So by which you can calculate, right? So this is the technique by which we are calculate. This is very high school level problem. We know this, how to calculate the mean, average. But let me write it in a different way. It is capital N. So you can write
Yes.
it like this. Okay.
Okay.
So it is, yeah.
Probability.
Okay. So in this way you can write. So this is the standard definition of mean. This is energy, that's why. If there is instead of energy, any quantity, let's say there is internal energy U or the enthalpy, any quantity may be there, it will be just HI here. Just like this, any quantity may be there. That's why this finding out this probability is very important. If you have probability, then you can calculate the average values. And why these average values are important, in the next classes that will be discussed, that these average values are basically these are from the molecular point of perspective. That means this is total a statistical result, and this average value, which we often by using the statistical mechanisms, that can be directly compared with our classical result. That means our internal energy or direct enthalpy, that we can calculate. That's why these average are important. Okay. Anyway, so this average value is given, that is this. 10 to the power
Epsilon.
minus, no, 1000 into epsilon, 10 to the power minus
This is
21.
not
It
clear.
is 10 to the power minus 18 is there. In epsilon, it is 10 to the power minus
Okay.
21.
Sorry. Sorry.
Mm. So the average energy is given as 1000 into epsilon. So now, if you use this formula, how you can write? How many energy levels are there? 3 energy levels. So it will be epsilon 0 P0, epsilon 1 P1, epsilon 2 P2. 3 energy levels will be there. Now epsilon 0 is 0, so that will not be contribute. Epsilon 1 is epsilon. So this is epsilon into P1 plus 2 epsilon into
2 epsilon into P2.
P2. So if you take common epsilon, so it is P1 plus 2 P2. Okay. So now what is
Okay.
the P1 and P2? This is N1 by capital N, and this is 2N2 by capital N. Correct? We have to
Correct.
find out the N. So you can write it that, so 1000 epsilon is essentially epsilon into uh, N1 into 2N2. So just it is N1 plus 2N2 divided by capital N. Okay. Okay, so epsilon will not be there. Yes. So now you have to calculate the N1 and N2. Then only you can calculate. Otherwise, how you can calculate the capital N? Because you
Yes.
two variables you need, right? Okay. So one more thing is there. Okay. This is 1000 epsilon. This is okay. One thing. Sorry. This value is given, right? This is the average energy. This is essentially the capital E. And this average, this energy is for a particular molecule. Okay. So there are how many numbers of molecules are there?
N.
N number. So you have to multiply that N. Otherwise, you can't get that. Okay. So you have to multiply it with multiply that value. So it will be essentially. Let me write it again clearly. Okay. So means I want to mean that this in capital is given as like this. Okay. That is essentially this. And these values we have figured it out. This is. This is the value. Which
The
what
n will be cancelled.
the n will be there will be a n, so n will be cancelled out. So essentially we have the equation that 1000 is equals to n1 plus 2n2. From here we have to find out what is the n1 and n2. Now how we can find out? We know n1 is the number of molecule at the
Ground
first
state.
ground, not ground state, in the first excited state. So what is our probability? That probability was, we know that pi, which is ni by capital N, it can be it can be written down as uh, Boltzmann fact. In the classes this was mentioned, right? Let me write. Okay, is this correct?
Okay.
How I can write it? Let me write. There was a term, if you can remember. This is the definition of probability. This is correct. This is in terms of the number of particle in a ith level and the total number of particle, that is capital N. But if you calculate in terms of energy, then what is the formula that we know? That is like that is called by Boltzmann distribution. Boltzmann distribution. That is, we know, if you want to consider a molecule, let's say for in I level, then it will be n0. N0 is ground level, e to the power minus beta into ni minus n0. Okay, so that is the formula that is discussed in the class. If you have any doubt, you can ask me. In this form, this formula is very important. This is a distribution formula. We will use several times.
The derivation of it important.
Yes, derivation is given also. Derivation was discussed in the class. Okay, derivation is also important. Okay, so now you can calculate the n1 and n2. N1 will be n0 into to the power minus beta. What is the sorry, energy? So what is the epsilon 1 and epsilon 0? Epsilon 0 is 0 and epsilon 1 was epsilon in this form.
Epsilon.
Hmm. So you can write it directly beta epsilon. And n2, it will be n0 into to the power minus beta
2 epsilon.
2 epsilon. So now it is clear. N1 plus 2 n2 will be n0 into the power minus beta epsilon plus 2 n0 into the power minus beta or 2 beta epsilon. And this value is given as, what is the value? It is
1000.
1000. 1000. Everything now you know. Beta is known. Beta is 1 by kBt. Kb is our Boltzmann constant. Value is 1.38 into 10 to the power minus 23. T is given 100 Kelvin. Energy is also given. That energy we have considered the value of energy as
1.3
this
10 to the power
10
minus
minus 21. Yes. So it is 1.3 into minus 21 joule. Just you have to put it. Then obviously you can calculate the n0. That will be 1000 divided by e to the power minus beta epsilon plus 2 e to the power minus 2 beta epsilon. You have to put these values. Okay, so if you put it, then you can easily calculate that n0 will be, I'm not doing this, this is just a mathematical calculation. It will be 1987. Do it, if if this does not come, then you can ask me in the next class, but this should come. Okay, n0 equals to
Okay.
1987. Now n1 and n2 you can calculate easily. What is the n1 and n2? This is the formula. So n1 will be n0 into the power minus beta epsilon. So it will be 731, and n2 will be n0 into to the power minus 2 beta epsilon. So it will be 268. Okay. So these are the number. So total number of molecule will be n0, n1, n2. So it will be 1987 plus 731 plus 268, which is essentially 2987. So this is a huge problem. I skip the calculation part, but you can do it by your own. But this will be a
Okay.
If there is any doubt remains, you can ask me in the next class, but this will be solved in this show. This part you can calculate. Otherwise, I did everything, but this numerical part you can calculate and check whether the values are matching or not. Okay, so it's already 5:55, so let's not consider any other questions. So if you have any doubt regarding the classes or this class, you can ask me. So how many questions we have discussed today? It is around 14. Okay, it's a good notice.
Which topics are important for this?
Topics means
Linked to this, I will study further.
I don't understand. Means books.
Books and which part I have to study for this in the books.
No, in the book you can follow Mercury, but that is very difficult to understand. It's better to first understand the lecture, video lecture, because you are in the first year of graduation, so it will be difficult for you to understand Mercury. But that is the standard book. Okay,
I only
the
had that book only.
you have only that book.
Yes,
You can try, but it is for me it was very difficult. Because they did not discuss the in between steps. They have just written down the formulas
yes,
like
yes.
this, and so that's why it's better to follow the lecture notes because I saw
And
the
the
lecture
lectures are
video.
in English also, so there is some problem.
That problem will be goes there, okay? Because you are just in first year. For me also it was a problem in talking in English, explaining in English, but uh, ये हो जाता है धीरे धीरे कोई दिक्कत नहीं है उसमें. You don't get tension about that, but first you have to understand science. If you understand the science, everything will be language will not create any barrier. So just go through the video lectures, and if you have any doubt regarding lectures or outside the lecture, any concept, you can ask me this tutorial session. And I will try to discuss something beyond which is taught in the last class or something also related to the last class. Some question I have discussed also some I discuss some part beyond that. So I will try to do like that. Okay. So further, if you have any question, you can WhatsApp me or mail me. You can do. Okay.
Okay, sir.
Okay, so let me stop here today. I will upload the video link and by tomorrow I will upload and also this lecture notes. This will be also uploaded in the weekly log sheet you have get from NPTEL that I will keep updating that. Okay.
Okay.
Okay, so let me stop my screen sharing first.
Next week, same time.
Uh, I don't know because I will be traveling next week. I will inform you. Okay, please write down my WhatsApp number. Let me write it. I I will I'll inform by mail. Okay, I will try to do it in the same timing, but if for only the next week, I'll be traveling, so probably 4 is difficult for me for next Sunday. Okay,
Okay.
in mail I will inform you, or let me write the chat. Where is the chat? I'm writing my WhatsApp number. You you can WhatsApp me. I will inform you. Okay, all of you.
Okay, sir.
Mm. Okay, is it visible?
Yes, sir.
Okay. Okay, so let me stop here today. I will share this.